A flywheel is a mechanical accumulator of kinetic energy, the principle of which has been known since ancient times, from the potter's wheel, where a rotating wheel accumulated the energy of the artisan's hands and ensured uniform motion, to 19th century steam engines, where massive flywheels smoothed the piston's movements. In the 20th century, it became a key element of internal combustion engines, and in the 21st century, it has evolved into a high-tech storage device, a superflywheel made of composites, capable of storing energy at tens of thousands of revolutions per minute. Today, such systems are used in the energy sector for grid balancing, in transportation for energy recovery, and in spacecraft as reaction wheels for precise attitude control, demonstrating the evolution from a simple wheel to a complex tool for future technologies. Back in the 1940s, Swiss engineers developed a new type of zero-emission electric bus that used a large rotating flywheel to store energy instead of batteries. The gyrobus was powered by an electric motor, which was powered by a generator that used a large rotating flywheel to store energy. The flywheel was rotated at charging stations using 3 arms mounted on the roof of the vehicle. When the flywheel reached its maximum speed of 3000 rpm, it was fully charged, and the bus could travel up to 6 km at speeds of up to 50 to 60 km per hour, depending on the load on the bus and the slope of the route. At one installation in Yverdon-les-Bains, vehicles sometimes traveled up to 10 km on a single charge. The flywheel used was quite large, 160 cm in diameter and heavy 1.5 tons, and was also placed in a sealed chamber filled with hydrogen under reduced pressure or with less resistance. Charging the flywheel from a standstill took up to 40 minutes, but after turning, adding additional energy to the flywheel took only 2 to 5 minutes. An electrical impulse is a short-term surge or jump in electrical voltage or current in a certain circuit or system, reflecting a rapid change over time. The analogy of an electrical impulse in the form of a kinetic impulse is used in mechanics in devices such as a crank press. The working tool of this press is a die. The pressing force is created by torque. In turn, the torque is made possible by an electric drive. The drive consists of an engine, a gearbox, brakes, a clutch and a flywheel. The electric motor rotates the flywheel, and due to the force of inertia, a torque is created on the crankshaft. Such a press can function both in step mode and in automatic mode. In this design, the flywheel plays the role of a kinetic capacitor, the power of which is measured by dynamic torque. In 2018 to 2019, I studied various flywheel rotation modes that allow for pulsed operation with low torque on the drive motor shaft. I conducted mathematical modulation based on the Chas-Campbell flywheel system. Later, I suggested that for single flywheels, it is more efficient to use intermittent generator operation. When the generator is turned off, the flywheel is accelerated using the drive motor. The engine operates in continuous mode, similar to a single stroke of a press. Instead of stamping, an electromagnetic generator is turned on, with a power regulator. This option was developed at the request of those who wanted to purchase such a flywheel generator for their own use. Unfortunately, due to the invasion of cannibals in Ukraine, the project was not completed. In my research, I also proposed a system where the generator is permanently connected to the load. This requires the use of 2 flywheels. The first is a large mass stabilizing flywheel connected to the generator, similar to the version used in the gyrobus. The second is an acceleration flywheel based on data I established during the research. This second flywheel accelerates to a moment of inertia where its potential exceeds the moment of inertia of the first flywheel with the generator. After acceleration, due to friction, the momentum of the acceleration flywheel is transferred to the rotation mode of the stabilizing flywheel. At a certain point, the kinetic chain is broken, and the acceleration flywheel accelerates again to a given kinetic capacity zone. The task is to push the stabilizing flywheel, which is effectively one with the generator rotor. The difficult part of this idea was to switch the kinetic node between the 2 flywheels. In 2025, I saw a proposal on Facebook for a similar design, where a powerful oil-cooled hydraulic gearbox was installed between two flywheels. Units with a capacity of 100 kilowatts to 1 MW were offered. It was visually clear that the engine control system was powered by a battery and had its own closed electrical circuit. Later, I learned about another episode regarding similar inertial generators, made in Turkey. A representative of a Ukrainian company made a small review. This time, I additionally received a simplified specification for a 1 MW unit. This data was enough for me to conduct a technical justification using my calculation method. Knowing the characteristics of the two flywheels, the electric motor, the generator, and the hydraulic transmission, I calculated and analyzed the kinetic chain for moments. All the basic requirements for the assembly model that I assumed were fully confirmed. I explained everything in great detail in the post and publication with examples and the calculation mechanism of such a design. Link under the video. The impossible becomes possible only by desire with the addition of appropriate costs.